An electron enters the region of a uniform electric field, as shown in the figure, with a horizontal velocity v equals 3 times 10 to the 6 meters per second. The uniform electric field, E equals 200 newtons per coulomb, is upward. The length of the plates is L equals 0.3 meters. What is the speed of the electron when it goes through the region and emerges from the electric field? So you can see in the image the electric field is going upwards, but since we're sending an electron, it's going to go in the opposite way as it gets repelled from all of the negative charges and attracted to all of the positive charges. And down here are some constants. So here is the elementary charge of an electron, which is the charge of one singular electron. And this is equal to minus 1.6 times 10 to the negative 19 power coulombs. And this will become important very soon. As well as the mass of the electron, which is 9.11 times 10 to the minus 31st power kilograms. This will also be used later. So if you look at this actually kind of looks a little like projectile motion, except instead of gravity, it's being pulled by the electromagnetic force. So we can solve this as we always do from problems involving projectile motion. First, we should figure out the time that it takes for it to travel from here all the way down to there. So to do this, we can use one of the kinematic equations, which says that the displacement is equal to the initial velocity times a certain time interval, plus 1/2 times the acceleration times t squared. So for this, let's focus on the x component. So it says it originally has a horizontal velocity. So we're going to be looking at the horizontal velocity when it initially enters. So there is going to be no acceleration in the horizontal direction because the electric field is vertical and it's not pulling on it from any angle. So we can ignore this whole side of the equation. So we simply get that the displacement of the charge in the horizontal direction is simply equal to the initial velocity of the charge horizontally times the time interval. So we can solve for t, and that equals the displacement divided by the initial velocity in the x direction, the horizontal velocity. So now all we need to do is plug in the numbers. And again, this displacement is simply L because it's going through the distance of the plates. If it's going purely horizontal, it's going 0.3 meters through the distance of the plates. So this is simply equal to 0.3 meters divided by the initial velocity. This is an equal sign of 3 times 10 to the 6th power meters per second. And if you evaluate this, you should get a value of 1 times 10 to the negative 7 seconds, which is a very small amount of time. So I think this is slightly smaller than a microsecond with like one extra zero. So this is the time it takes for it to pass from this end of the plate to the other end of the plate. And it does this in a very fast time. But we're not solving for time. We need to find it when it actually emerges from the electric field, the speed. So to do that, we also need to find the y component of the velocity, or the vertical component of the velocity. So I'm going to erase all of this for now. So we calculated that the time interval is equal to 1 times 10 to the minus 7 seconds. Now we need to calculate the velocity, vertical velocity. So to do that, we should probably first calculate the acceleration of the charge in the vertical direction. And an acceleration is produced when there's a force applied. So you can probably see where this is going. We need to figure out the force from the electric field. So we know that the electric field is defined as the force per coulomb, or the force per single charge. And solving for force, you get that the force is equal to the electric field times the charge. This is simply manipulating the equation. And so now all we need to do is just plug everything in for the force. Force is equal to the strength of the electric field of 200 newtons per coulomb. And the amount of coulombs is given by the charge of a singular electron, which is minus 1.6 times 10 to the negative 19th power coulombs. So if you evaluate this, the force is equal to 3.2 times 10 to the negative 17th power newtons. It is a really, really, really small force. So there's that. So now that we figured out the force, we can calculate the acceleration using Newton's second law. The net force is equal to mass times acceleration. And in this case, the only force acting on it is the force from the electric field. So we don't have to worry about the net force. So get that. The acceleration is simply the force divided by the mass. And in this case, the mass is the mass of the singular electron. So a really tiny mass. So again, we plug everything in. 17 newtons divided by mass of the electron of 9.11 times 10 to the minus 31st power kilograms. And then if you solve for that, you should get that is about the acceleration in the y direction is going to be about minus 3.51 times 10 to the 13th meters per second squared. So now this is really big. So that's a really large acceleration now. So that's the acceleration in the y direction. So we've managed to calculate the acceleration in the y direction. And again, the negative sign just means that it's going down, since we've established up as positive, as up as the positive y direction and right as the positive x direction, just like how a normal coordinate system would be like. So now we have calculated the acceleration, which I'm just going to round to this. So now we can use our other kinematic equation. The final velocity equals the initial velocity plus an applied acceleration over a period of time. And vertically, it initially is just moving horizontally. So the initial velocity in the y direction is 0 meters per second. It only gives us the horizontal velocity when it starts moving. So we can ignore this whole part. Get rid of that. So the final velocity in the y direction simply equal to the acceleration in the y direction times the time interval. Time is something that they both have in common, just like in projectile motion. Should probably write this a little smaller. So now all we need to do is just plug everything in. I'm just going to drop the f subscript. Equal to the acceleration 3.51 times 10 to the 13th power meters per second squared times the really small time interval of 1 times 10 to the minus 7 seconds. Now if you evaluate this, you should get that it is, let me see, about minus is equal to minus 3.51 times 10 to the 6th power meters per second. So now this is really fast again. And this is actually about minus 3.51 million meters per second. So yeah, really fast. Okay, so now that we have this, we have the, sorry, some more stuff. We have that, we calculated that the final y velocity is equal to minus 3.51 times 10 to the 6th power meters per second. And the final velocity in the x direction, or in the horizontal direction, stays the same. It's 3 times 10 to the 6th meters per second. And yeah, So this stays the same. There was no acceleration acting in the horizontal direction at all. So now to calculate the speed of the electron, we're just simply finding the magnitude of the total magnitude of the two. So this is simply the square root of the x velocity squared plus the y velocity squared. It's like the distance formula. You have an x component, you have a y component, so the total speed will be the hypotenuse. So now all we need to do is just simply plug everything in. So we get that it is equal to the square root of 3 times 10 to the 6 meters per second squared plus minus 3.51 times 10 to the 6 squared, and square root that whole thing. And now if you solve this, you should get that the speed of the electron when it goes through the region is about 4.62 times 10 to the 6th power meters per second. And this is the final speed as the electron exits the field.